Okay, you guys should have just spent a little bit of time looking at basically figuring out how to reverse differentiation. You're trying to find a function whose derivative is a particular function. So if we have an example like this, find a function whose derivative is f of x equals 5x to the fourth. So you probably, hopefully, discovered sort of a rule where you're taking that exponent and you're increasing it by 1. So if I did 4 plus 1, that would give me 5. And then I'm dividing out front by that value here. So if I do 5 divided by 5, I would just get a 1 right there, which I don't have to write. Notation-wise, whenever we integrate a function, a lot of times we'll use the capital letter of that function to show that we have reversed that derivative there. So I would use like a capital F of x, just some little notation here. Like I would say here that the derivative of capital F of x would be lowercase f of x. That's just notation that you'll see a lot of times. So it is true that this is possible for an answer. Certainly, if we take our derivative here, if we take the derivative capital F prime of x, or we could call it lowercase f of x, here we would get 5x to the fourth. So this is a possibility. But there are a lot of other possibilities. In fact, there's infinite possibilities because there are many other functions that also have the same derivative. For example, f of x could be x to the fifth minus 10. Okay, the derivative of this would still be 5x to the fourth, because the derivative of that minus 10 would just be 0. I also could have f of x equals x to the fifth plus 107. Right? Still, my derivative here would be 5x to the fourth. So basically, you should be seeing here that I can add or subtract any number that I would like onto the end of this. As long as it's just a constant, it's still going to give us the same derivative of 5x to the fourth. So what we're going to do for this when we take these when we take these antiderivatives, when we reverse the differentiation process, we are going to use that rule that you guys were starting to see, and we will get x to the fifth, but we can put plus capital C. Okay? And capital C is the standard letter that we use to represent a constant in integration problems. So every time you do infinite integration, you want to put this plus C over here on the end. And down here you just see a notation. F of x is an antiderivative of f of x on an interval if capital F prime of x equals f of x for all x in whatever that interval is. We call this infinite integration because there are infinite number of possibilities for your function here, because c could have infinite different values. Okay, so I want to look at a little bit of notation that we have used before. So we have talked about a derivative being something like dy over dx equals, and let's just pick 5x to the fourth like we were dealing with before. So some notation that you're going to see whenever we're dealing with intervals or antiderivatives, those are going to be used interchangeably, is that we're going to see we've got a dy over dx. This is the derivative of y with respect to x. So we have to say what variable we're taking the derivative with respect to. Remember, on related rates, that wasn't x, that was a t most of the time. So, so if I want to solve this equation right here for y, I have to get rid of everything on that left-hand side that doesn't deal with a y. So I would multiply both sides by the dx like so. And that would give me dy equals 5x to the fourth dx. And so then, to get rid of this derivative of y, I would do the integral. And we'll talk a little bit more about those, about that here in a second. But it's like we have a 1 right here. So So this was just going to give us a y on this side. And then over here, of course, we'd raise that exponent by 1. It'd give us x to the 5th. And we would divide out front by the 5 and get just a 1 there like we saw before. And we would put a plus c whenever we integrate. So whenever we look at integrals, we're going to see some different parts that we are going to use. When we have our integral here, we will see that the different parts that we see here, we have our integration symbol. We have, here of course is just our function. And for this part, this dx here, this is just our variable of integration. That variable of integration is important to have there because it can change what your answer looks like. Let me give you a couple of examples that look almost the same but are going to be different. So if I am integrating k dx versus integrating k dk. Okay, so the first integral that I see here tells me that I'm integrating k and that x is my variable of integration. So if x is my variable of integration, k just must be a constant in this case. So I would just get k times x, and of course I put the plus c over here on the end. However, if I have k dk, this means k is my variable of integration. So k is not a constant. K is like k to the first power. And I would need to raise my exponent by 1. So that would give me 2 there. And I would need to divide the coefficient out front by that exponent, which will give me 1/2. And then just like the others, I'll put the plus c over here on the end. So you can see the difference in having a dx and a dk there. So it is important for it to be there. It's going to feel like, especially at the beginning, that it's really not that important to write this, but it does make a difference in some instances. So let's just do a few problems. For each of these, find the antiderivative, which we're going to call capital F of x, for each function f of x. So when you have a constant, sometimes this will confuse students, but it's just like you have 0 x's there. So you're going to raise your exponent by 1 and then divide out front by that 1. And this will be your capital F of x. Make sure you always put the plus c on the end. So this is going to be capital F of x equals 8x plus c. You must have the plus c on the end. Don't forget it. Whenever we integrate 0, here again, you could think like there's 0 x's there. So if you raise your exponent by 1, you would get this. But out front, you would just still have 0 over 1. And then you would put the plus c. Well, 0 times anything is going to still be 0. So this is going to equal 0 plus c, which we would just get c. Oh, sorry, f of x equals c for that. So if you are integrating 0, you'll just get that constant of integration. For number 3 here, we've got 1x right there. Here we've got 0 x's. So for each term here, we want to raise our exponent by 1, and we are dividing out front. Dividing out front by that exponent. Skipping to the answer when I shouldn't. And over here, we would raise the exponent by 1, divide out front by the exponent. I'm going overboard on showing work here just to be sure that it's clear what I'm doing. I would normally just skip straight to the answer, 5x squared plus 3x. And I'm forgetting my plus c. Must always put that plus c with it. So if we look at example 4 here, again, we are raising that exponent by 1. That gives me x to the 4th. Then I'm dividing out front by that exponent, so I got 4 over 4 here. Here I'm raising my exponent by 1. That'll give me 2. I'm dividing out front by that exponent. And then here I don't have any x's, so I'm raising the exponent by 1, dividing out front by that new exponent. So again, you don't really need to write that step. I just want to be very clear what I'm doing. So I'd have x to the 4th minus 3x squared plus 2x. Plus c, I should always have that plus c there. Alright, so if we do example 5 here, I'm going to quit showing excessive work this time. You would have x to the 5th. You would divide 40 by 5, which would give you 8. Then for the next one, you would have x to the 3rd. You do 27 divided by 3, which would give you 9. And then you would have 10x, and don't forget to put the plus c on the end. Every problem needs to have that plus c on the end. For a problem like number 6, we don't have any rules for like a quotient rule here. So we need to change this to negative exponents before we try to integrate. So we would do negative 2x to the negative 3 plus 3 here. And whenever we integrate for this, we would raise our exponent by 1, which would give me x to the negative 2 power. And then I would divide my coefficient out here by that new exponent, by that negative 2. And then I'd get the 3x over here on the end, and I'd put a plus c. So this would give me x to the negative 2 plus 3x plus c. You may also see them put this negative exponent back in the denominator, so you'll have 1 over x squared plus 3x plus c for that one. Okay, so on the next slide, you just have a recap of some of these rules. So over here, I have our differentiation rules. So if we have the derivative of a constant, we just get 0. If we integrate 0, we get a constant. You're seeing that these are opposites here. Fundamental theorem of calculus that we have already learned. If I take the derivative of a constant times x, I just get that constant. If I integrate a constant, then I will get that constant times x plus c. Notice all these have plus c's here. If I take the derivative of two functions that are separated by a plus or minus sign, I can just take the derivative of the first and then add or subtract the derivative of the last. In a similar manner, I can also split integrals apart that same way. We really already talked about this in the video about the properties of integrals. And then at last, the rule for a derivative is that I will subtract 1 from my exponent, and then, multiply out front by my exponent and then subtract 1 from it. So for my rule for integration is going to undo both of those things. So first you will add 1 to your exponent, and then you will divide by that exponent increased by 1, which you can see written this way, or it could be made a fraction, like here. So this is sort of like formal notation for that rule for integrating. So you are going to see some problems from your book that ask you to solve each differential equation. This is just going to go back to that notation I was talking about at first. If you're solving these differential equations, you would first need to get the dx over here on this side, so that all the y stuff is over here on the left, and all the x stuff is over here on the right. And then if you integrate on this side, this is just like 1 dy. You're integrating with respect to y. You have a coefficient of 1 there. This just gives you y. Okay. And then over here, we're integrating 5x. So we will raise x to the 2nd power. And then we've got to do 5 divided by that new exponent, which is 2. So 5/2 x squared, and we're going to put a plus c on the end there. So essentially, it's just asking you, as long as it's just dy dx, and it will be for these problems, it's just asking you to integrate this value over here. If you don't show every step like so, if you don't show the step where you take your derivative of this side and take your integral of this side, and you've got 8x to the third plus 9x squared minus 4 dx with the integral symbol, it's going to be okay at this point, but when we get to solving differential equations, we'll have to think about it a little bit more because there will be x's and y's. So over here, we'll just get y, and then over here we'll get x to the fourth. 8 divided by 4 is going to be 2. Over here we'll get x to the third. 9 divided by 3 is going to be 3, and they'll have a minus 4x, and always put that plus c there on the end. Okay. There are a few more that are going to be a little bit trickier to deal with, not too terrible. Example 9 is not really one of those. For example 9, whenever you're asked to integrate this, you're just going to have 3x minus, here we'll have x squared, we'll do 5/2, and then over here we'll get x to the third, and we'll have 7 thirds, and then make sure you always put a plus c there on the end. Whenever we're looking at problems like example 10, we're not going to be able to do this problem unless we change it to fractional exponents first. So this would be the same as integrating x to the 1/2 dx. So the rule remains the same, it's just a little bit harder to accomplish. We're going to add 1 to our exponent, which will give us 3/2. And then we don't have a coefficient, so our coefficient is just 1. We have to divide by that 3/2. Now, and make sure you put the plus c. Now, dividing fractions is easy as pie. We're going to flip the second and multiply, so when we do that, we're doing 1 times 2 thirds, and we'll just have 2 thirds x to the 3/2 plus c. For that, you might see them change this back to a root. If you do, it's going to be 2 thirds square root of x cubed plus c. For our last couple problems here, if you have a fraction like this, you need to switch this to negative exponents first. So we'll have x to the -4 dx. So to integrate here, same rule. We increase our exponent by 1, which will give us -3. We want to divide out front by that -3. So we'll end up with a -1/3 x to the -3 plus c. You may see this written as -1/3x to the third plus c. They may move those negative exponents back down to the bottom. 12 looks initially like a problem that we cannot do, but for 12, we can use the love connection for this one. So whenever we integrate, we're going to have x over, I'm going to write this as x to the 1/2 plus 5 over x to the 1/2. And then if I just convert these so that they are a single exponent, I'll have x to the 1 minus 1/2 will just give me 1/2. And then I'm going to get 5x to the -1/2. So hold on to my dx there on the end. So now I have this rewritten where I can use the just basic power rule for integrating. So I will do x to the 3/2, and we just did this. 1 divided by 3/2 is going to be 2 thirds there. And then I'll have x to the positive 1/2, and I've got to do 5 divided by 1/2, which seems like it should be 2.5, but it's not. 5 divided by 1/2 is 10, so it's going to look like this. 2 thirds x to the 3/2 plus 10x to the 1/2 plus c. So you are going to do some practice with these from your textbook. So here is your assignment. If you finish this early, work on your free response questions.